Assalamualaikum and good day to everyone. Today we're going to continue with our chapter 3, starting with part 3, general vector spaces. Okay, as you can see here, last week we already discussed a few topics in chapter 3, which is vector space and two-dimension. Today we're going to start with part 3 and 4, where we will discuss on row space, column space, null space, basis for metric and basis for vector space in this part 3. Next we will have part 4, which is coordinates in change of basis. We will start with the definition of row and column vectors. As we can see, for an m by n matrix like this one, matrix A, the vectors in Rn form from the rows of A, means that the rows of A, this is the first row, the second row, until the nth row, like this, are called the row vectors of A. So it is called row vector. Meanwhile, in Rm, formed from the columns of A, before this row, now columns of A are called the column vectors of A. You can see the column here, this is the first column, second column, and the nth column. Look at our example. We have matrix A here, 2, 1, 0, 3, negative 1, 4. To identify the row vectors, we see the row here. Each row we have, so we have two rows, row 1 and row 2, the vectors. So row 1 is 2, 1, 0, row 2 is 3, negative 1, 4. For the column vectors of A, we see we have first column, second column, and the third column. So we have the first column is 2, 3, and then 1, negative 1, and then 0 and 4. Now we come to the part where we will identify the row space, column space, and null space. Definition and example. If A is an m by n matrix, then the subspace of Rn spanned by the row vectors of A is called the row space of A, and the subspace of Rm spanned by the column vectors of A is called the column space of A. See the example that they give us here. They give us 2 by 3 matrix A, which is 1, 5, 3 and 2, 6, 1. How to find the row space of A? Now, again, based from the previous slide, we learned that we have two rows here, right? So two rows, just write it back down. 1, 5, 3 plus 2, 6, 2. And then we put a scala 1 and scala 2. And both C1 and C2 belongs to real number. Then you can plus them. C1, 1 plus 2, 5 plus 6, and 3 plus 2. And you will get your row space. Okay, now how to find the column space? Again, same with previous row space. We state each of the column vector here. The first vector is 1, 2, and then followed by 5, 6, followed by 3, 2. As you can see, we will have one more scala compared to our row. So this will be C1, this will be C2, this will be our C3. Solving this will give us the column space of A. You can see here 1 plus 5 plus 3, 2 plus 6 and plus 2, where all the scala is a real number. Okay, row space actually is a set of row vectors, and column space is a set of column vectors. In general, the row space and column space of a given matrix is different based from what matrix given to you. Now we come to the next one, which is null space of a matrix. Let's say A be an M by N matrix. The solution space of the homogeneous system, please recall back what is homogeneous system based from our previous class, of equation Ax equal to 0, which is subspace of Rn, is called the null space of A. Basically, we must find the x here. X equals to what? Because it is homogeneous system, Ax equal to 0. So the A is our matrices, we need to find the x. The x here is the null space of A. Example here given. Given an M by N matrix A, so M by N matrix A, the vector space consists of all possible solutions of Ax equal to 0. It's called the null space of A. So we have our A, then we must find the x here, and it is equals to 0, right? So we need to solve this as a linear system. How we do that? Now we change to augmented matrix. Solve the Ax equal to 0 by using augmented matrix. We need to recall back what we learned about augmented matrix and linear system based from our chapter 1 and chapter 2. So we do the Gaussian elimination here. We will not go into details how we do the Gaussian elimination. I think you should probably go back to the previous videos to understand what I'm doing here, the row operations and everything. Okay, so we simplified it. After doing the row operations, the Gaussian elimination, we get our row echelon form here. So based from this answer, we get our answer of x3 is equals to 1 based from this answer. Okay, and then our x2 is negative x3, our x1 is 2x3. So this is our x2, x1, and this is our x3. Okay, then you make into this form. So we have x1 which is 2x3, x2 which is negative x3, x3 which is x3 1, right? And then we take out the x3, then we will get our answer for the null space of A, which is equals to 2, negative 1, and 1, where x3 is a free variables. Now we come to the next part, which is basis for matrix. There are two things: basis for row space and basis for column space. Now we start with basis for row space. Let A here is an M by N matrix, and matrix E is in row echelon form of A. So we have matrix A, and then we have matrix E. We change it to matrix E, which is in row echelon form using Gaussian usually. So the row vectors with leading ones, the non-zero row vector of matrix E, will form a basis for the row space of A. Okay, so we must make the Gaussian elimination into row echelon form with leading ones, and then the non-zero row vector, which is not all of it is 0, must have a number besides 0, of matrix E will form a basis for the row space of A. Matrix A is in row echelon form. Let's see our first example. They give us matrix R, and as you can see, matrix R currently is in already row echelon form, and it already have leading ones. Remember, we need to deduce the matrix into row echelon form with leading ones. Okay, now we identify the non-zero vectors. So if you look into the matrix, the non-zero vectors, we have 3 here, 1, 2, 3. This one is all 0, so it's not a non-zero vector. So just from the vectors, we can say that we have 3 rows, R1, R2, and R3, and you state back the numbers, the matrix. Okay, these 3 rows will form a basis for the row space of R, the row space of matrix R. Let's look at our second example. They give us matrix A, but as you can see here, compared to the previous example, this is not in row echelon form. So we must change it. We must change it into row echelon form with leading 1. Okay, with leading 1. We change it to leading 1 using Gaussian elimination here. So after doing the steps, the row operations, we will get our new matrix. Let's say here A will be matrix E here, that already have a row echelon form. Same matrix, but E here is given because it already have row echelon form with leading ones. Leading 1 here. Okay. Now the next step is to look into the non-zero row. So this is non-zero row, this is a non-zero row, this is a non-zero row, but this one is not a non-zero row. Then after finding the non-zero row vectors, it will form a basis for the row space of E, hence form a basis for the row space of A. So as we can see, row 1, row 2, and row 3 here is based from our finding before of the row. Let's move to the second one, which is basis for a column space. Let A is an m by n matrix and E is in row echelon form of A. So this is basically same as our previous row space. Okay. Then the column vectors with leading ones, again we must deduce into leading ones of the row vectors form a basis for the column space of E. Then the corresponding column vector of A will form a basis for the column space of A. Next slide we will see what this means. Now we look to our first example. Here again they give us the matrix R, and as we can see here, the matrix is in row echelon form with leading ones. So these are our leading ones. The vectors that contain the leading ones will form a basis for the column space of R. So this is R. So the vectors that consist of leading ones will be the basis of the weight. Okay. So we have our first column here, 1, second column 2, and then the fourth column here, C4. So this is our this is our basis for this column space of R. C1, C2, and C3. Let's look at our next example, example 2. They give us matrix A, but as we can see, this matrix is not in row echelon form. So what we must do, we must change this matrix to matrix A that is in row echelon form by using our Gaussian eliminations, row operations. Okay, so as we can see in the matrix E now, we have our row echelon forms. And look at the leading lines there. The leading ones there. We have 1, 2, and 3. So these 3 columns here, we must take note of the place here. We have, this is our C1, C2, C3, C4, and C5. So this number here, remember in the first slide of column space, they are a bit different. That I will explain here. This is the difference between the row and the column. For the column, these 3 is the row, is the column space for matrix E, not matrix A, for matrix E. How to find the column space for matrix A? So we take note of the C1, C3, and C5. We look back into our matrix A and find the C1, C3, and C5. Then we can get, this is our C1, this is our C3, this is our C5. These 3 columns. If the question asks you to find the column space for matrix A, you must look back from the position in matrix E here, and then look back into the position in the matrix A. So the C1, C2, and C3 here in the matrix A will be the column space. Column space for matrix. Column space for matrix A. This 3 is the column space for matrix E. Alright, based from the explanation from the previous slides, so you can see here, since the first, third, and fifth column of E contains a leading ones, this is E here, matrix E of the row vectors, the vectors here 1, 3, 5 form a basis for column space E. Remember, basis for column space E, which is in the row echelon form here. But it is not yet, we do not find yet the basis for columns, for the column space of matrix A. We do not find it yet. Alright, to find the basis for column space of A, you need to use this first, third, and fifth column, and then look back in matrix A, what is the value of the first, third, and fifth column. Then we can say it is a basis for column space A. when we go back and see matrix A, we can find the corresponding column vectors at first, third, and fifth column, which are this one here, this value, this is the C1, the C3, and the C4, and then it will form a basis for the column space of A. So that is the difference between the row space and the column space, where for the row space you can directly find the basis of E, same with basis of A, but in column space you must look back at the corresponding column vectors in order to find each of the basis of A. You need to look back. We cannot use the same as the matrix E. Now we come to the slide where we will discuss about dimension and rank. Okay, we have two here, dimension of row space of A and dimension of the column space of A. The dimensions also called the rank of A. So basically some question will ask about rank, some question will ask about dimension. Okay, basically it's the same thing. We look to the dimension of row space, the number of non-zero rows in the echelon form of A. So the number of bases for row space. This will become the number of bases for row space. As we know before, the non-zero rows become the basis for row space. The dimension of column space is number of leading ones in the echelon form of A, still in the form of A. So the number of bases for column space is based on the leading ones. Number of bases for column space is based on the leading one. If you remember the previous part where we discussed about dimension of row space, dimension of column space of A. Alright, so basically for column space, you need to find the row echelon form of A. If it is not in row echelon form, then you must refer back to A for the basis, not the basis on E. Then you can see the dimension of A in the column space of A. Let's look at our first example, rank of matrices here. They ask us to determine the rank and basis of the row space of matrix. Here is matrix A. As we know, we must change it to the row echelon form. Okay, this is not in row echelon form. So we reduce to the echelon forms of A, which is here. We call it matrix E. Okay. Then the rank A is equal to 2. Because of what? Because of the non-zero row here. We have two non-zero rows, right? So these two is our basis, V1 and V2. And the dimension is the number of bases we have, which is 2. Let's look at the second example. Now they give us a matrix of A, but this is not in row echelon form. So they ask us to find the basis for row space and the basis for column space. Then based from the basis of these two, we find the rank. First, again, we need to change this to row echelon form with leading ones using Gaussian elimination. Then we can continue finding basis for number 1 here, the row, and basis for number 2 here, column, and then the rank. This example show you the step-by-step in changing the row echelon form towards the row echelon form here. So we do the row operations until we get our leading ones. Alright, so here we have this and this, the columns. This one is column 1 and column 3 as our leading ones. Then from this we can already see actually what is our basis for row space, which is number of non-zero. And we can see the column that we need to take note, column of the that include the leading ones here, which is column 1 and column 3, and we need to look back at the corresponding matrix A to find the basis for matrix A, which is column 1 and column 3. And as I mentioned, this slide shows the basis for row space of matrix. So for row space, we just add the non-zero value into, list them into here is R1, row space 1, and row space 2. It is straightforward based from our previous example. For column space, we know that this is our leading one, C1, C3, but for matrix A, we cannot take this value. For matrix A, we need to look back towards the column in the matrix A and identify the column. For this one is C1 and C3, and this will be the basis for this basis for column space A here. The rank is 2. Here we have C1 and C2. The basis is the rank. Okay, the basis for column space and the basis for row space is 2, and the rank should be 2. You cannot have column space with different value than the row space for rank. It must have the same number of bases, okay, for each of the matrix. The number of bases for column and the number of bases for row space must be the same. For this one we have 2, right? Because previously we know that the row space is 2. Now the column space is also 2, and the rank or dimension is 2. Now we come to the part where we want to find the basis for our vector space. How to find it? We will start with the basis for a row space, then we will cover the basis for our column space. Now, suppose you are given a vector space V which is spanned by a set of row vectors. We have, let's say here, V1, V2 until Vm set of row vectors. What you need to do is you need to form a matrix A here. Okay, based from this vector, we form your matrix. Let's say here the first row is V1, so the first row will be our V1. Second row V2, and then until our Vms. Okay, you form a matrix first. After you form the matrix, you need to reduce the matrix to our row echelon form. Then it will yield the row echelon form E, same as before. Remember, in the previous part we got our matrix, but from now we have vectors. We change our vectors to matrix A, and then we make into matrix E, which is our row echelon form matrix. Then from this matrix E, we obtain the important rules as follows. 3 important rules that we obtain from the matrix A. First is vector space V is the row space of A. Okay, so the row space of A is the vector space of V. The dimension of V equals to the dimension of row space of A and equals also to rank of A. Alright, the third one, the basis for row space vector of V equals to the non-zero vector in the echelon form of A. I think you're already familiar with this based from our previous part, where we see that the basis is directly from the non-zero row vectors in the echelon form of A. Alright, but the column is different. The row you can take directly, but the column is different. Okay, let's look at our example. Find the dimension, rank, and set of bases for row space vectors for the row space V spanned by this for vector here. Okay, as I mentioned before, the first thing we need to do is we need to identify the vector here, the 4 vectors, and then change the form into a metric form. Now we use A as the name, so we change the vector space V towards form matrix of A, where you insert your V1, V2, V3 and V4 into the matrix. Then using the elementary rows, we change it into the row echelon form using Gaussian, right, with leading 1. Okay, then you can have the answer here. I will not explain in detail on how we get this. So basically you do row operation from this, we come to this, and then we change it into this until you get the final version where we have our leading ones. This is the first leading one, second leading ones, and the third leading ones. And of course, for the dimensions, it is based from the what is non-zero here for the row, right? So dimension, we have dimension 1, 2, and 3 because this is the basis here. First row is a non-zero row, non-zero row number 2, non-zero row number 3. So the dimension is 3, and the set of bases for row space we take directly from our E here. This is basically our E, right? So we take directly from that, where this is the first row, this is the second row, and this is the third row. Now we come to the basis for a column space. Suppose given a vector space V spanned by a set of column vectors. This is not row vectors, it's a column vectors because of this transpose. Right? This is, they make it transpose, so it's supposed to be like this. But if you transpose, it will become like this. Right? Remember this T, transpose. Then it is not, which are not necessarily linear independent. It is not necessarily a linear independent, these column vectors. Same as our row space, we form a matrix A having the vector as a column vector. So we can see this is our V1 here, first column, V2, the second column, and then so on, Vn. Okay, so we make it into the column. Instead of before this a row, we make it into a row. Now because it's column space, we make it into column. By reducing the matrix to row echelon form, it yields the row echelon form E. Okay, you get your E, and then you can identify the column in E that contain leading ones. So E basically your row echelon form matrix. The important rules obtained as follows. Dimension of V is equal to dimension of column space A, and also equals to the rank of A. Okay, dimension of V, dimension you get, is the dimension of column space of A and also equals to rank A. Second one, the basis for vector spanned by the V1, V2 until Vn equals to the corresponding column vector of A. Means that it is correspond to the previous vector A. You cannot get directly from your vector E. Right, same as what we have discussed in our previous part. We look at the example now. They ask us to find the dimension and set of basis vectors for the vector space V that is spanned by these 5 vectors here, V1, V2, V3, V4 and V5. So what you need to do, first thing is, this is a column, right? So we need to make it into 4 matrix. This 1, 0, 1, vector 1, 1, 0, 1, 1, vector 2, 1, 1, 2, vector 3, 1, 2, 1, vector 4, and negative 1, 1, negative 2 as your vector number 5. Then, of course, we need to change it to our E, which is the row echelon form format. Okay, we need to change this first to row echelon form with leading 1. Then, okay, by using the elementary row operations, we obtained from this to this. We do the row operation, this to this, until you get your row echelon form format with leading 1. Okay, this is our E here. The dimension of V is 3. Why? Because of the leading number here. 1, leading 1 here. We have 3. So this is our leading ones that occur in column 1, column 2, and column 4. So the dimension is, directly you can see, is 3. Okay, based from our observation in the row echelon form matrices. Remember, for column space, we need to look back at our A here, find our column 1, column 2, and column 4, which is our leading lines, leading 1 in our row echelon form matrices. Okay, so when you find it, the basis for the column space spanned by V1, V2, V3, V4, and V5 is this C1, C2, and C4. We take the value from our matrix A, the corresponding column, not the column that we find when we do our row echelon form. Alright, that's the main difference, I think, based from a few parts that we learned here. The main difference between calculating the row space and column space for our matrix, from the matrix. Now we come to nullity. What is nullity? And the example of nullity. Okay, nullity of matrix A defined as dimension of the null space of A. This is the dimension of the null space of A. For example, find the nullity of our matrix A here. So the solution is, first you must know that the null space of A can be found by solving Ax equal to 0, where x here transpose means that it is a column actually, x1, x2, x3, and x4. So actually you should have equal to 0. This is the simplified version. If you want to solve this one, this is simplified version. You should have, if you want to solve it in this form, this is our A, and it should be equals to 0. You should have one line like this equal to 0. So after this you can solve it like this if you prefer to have your 0 here. This example, I think they think that you are expert already, so you already know that you have 0 here. But for those of you who still want to do it properly, then put the 0 after the metric, because you are solving this ax equals to 0 actually. Okay, then we use elementary row operations to change it into our metric here, into this form, the row echelon form, okay, with leading 1. Alright, if you do it properly, you will have this one and you have 0 here, because it is ax equal to 0. Okay, now where is the leading line? Leading line is in the first column, the second column, and the third column, and the fourth column, sorry, and our third column here is a free variables. X3 is free variables. So how you find x4 equals to 0 here? See our x4, this is our x4, is equals to 0. So x4 is 0. What about our x2? Okay, x3 here we give a variables. Let's say for this one we give our x3 is equals to t. We can give a variables to our parameter to our x3. Now finding x2, here we move this to over here, so we will find 3 minus 2x only, because we know that x4 is 0, so this is 0, so negative 3 over 2 go here will be 3 over 2x, 3 over 2 x3, okay, because this is x3 is our t here. Then to find x1, these two we move to the right side here. This will be 0 because x4 is 0, and our x2 is x2 here, negative 2 over here is negative 2 column 3 over 2 x3. This is our x1, and when you multiply it you will get x1 equals to negative 3 x3. After you solve that, we can, for this question they give the parameter for x3 is s. Before this, in previous slide I gave it c, so, but we follow this example. Okay, now this is the x1, x2, x3 and x4, and we already found all of the values here. We found x4 is 0, x3 is s because it is a free variables, x2 is 3 over 2 s, and x1 is negative 3s. Okay, refer to the previous slide for explanation on this. So we can bring the s out here, and then we can find our basis of the null space of A, which is this negative 3, 1 over 5, and 1. This 1, 0. This is our basis of the null space A. The nullity of A is the dimension here, which is 1. Okay, let's look at our next example. They ask us to find a basis for the null space of A. They give us matrix A here, but as we know, the null space of A is the solution space of the homogeneous system, Ax equals to 0. So it is actually in this format, 2x1 plus 2x2, x1, x2, x3, x4, and x5, right? So we must make, for you to better understand here, you can make 0 to signify this 0 at the right hand side here. Okay, so you see in the last row here we have the solution in the reduced row echelon form. This question do the row operation until reduced row echelon form, but you can just make the solution into row echelon form only, just like previous example. Okay, this can save you time because of the row operations, as you know that reduced row operation take a longer time to finish, so you can just make into the row echelon form with the leading one. Alright, so but for this question they use until reduced row echelon form, and as we can see here we have our leading one in our, this is x1, x2, x3. Okay, this equals to 0 here. So we have our x2, let's say it is s, and our x4, x5, sorry, x5, this is a free variable. Okay, we give it t, for example. Then solve for the remaining three x here, x2, x5, let's say x4 is equals to 0 here, x4, 0, right? It's nothing here. For x3 is equals to, this one 1 is our x5, right? x5 is t, so t move here, -1, which is negative t. Okay, and for x1 is equals to, this is t, this is our t, and this is our s, right? x2, s. So we move to the right, both of them, and then we get negative s, negative t is our x1. Then from this we can find our basis for our nullity. Now we continue with making x into this format where we have x and our x1, x2, x3, x4 and x5. So based from previous slide, we understand that we have our x1 is equal to negative s, negative t, our x2 s, our x3 is negative 3t, x4 is 0, x5 is t. Okay, they use this s and t. So because it is s and t, you change into 2, right? One for the s, one for the t, and then from this you will get your basis of the nullity here. These two, we have 2 here. Okay, s and t as our scalar. Again, based from the previous slide, we know already that the vectors v1 and v2, as mentioned here, form a basis for the null space of A. Okay, and what about the nullity of A? Nullity dimension here is 2, because we have this 1 v1 and 2 v2, and we get our basis and nullity for matrix A. If you look closely, if matrix A here has n columns, then if you add rank and nullity here, you will get your n for the matrix. Rank, as we know, is a number of leading variables. So how many lead one we have, alright, leading one. And then nullity is number of free variables, free parameters. Okay, if you plus both, add both, you should get your n for your matrices. Okay, if you look closely, you go back to the previous slides, you go back how to we calculate the rank, what is needed for rank and what is needed for nullity. It is actually number of leading variables plus number of free variables, the rank plus nullity, and you will get your n's for each of your matrix. Now we come to the exercise part. We have, this is our first exercise. Find the rank and nullity of the matrix. They give you matrix A. Okay, I want you to solve this. Okay, we will discuss in our next class. Right, make sure you do this rank and nullity for this matrix. And then exercise number 2, we have 2 types here. One, the given matrix is in row echelon form already, and find the basis for the row and column spaces of A. We have 2 here, A and B, This is in row echelon forms. And the second one is they give you not in row echelon form. Again, the same equation. Find the base for the row and column spaces for A. Okay, I want you to complete these two exercises. Alright, and as usual, we will discuss the exercise in our next class.